Different people have made different trade-offs, and that's really what we're going to be talking about today is here are the trade-offs that we made, here are the choices that we made, here's why we did them, and here's the benefits that we get for our customers and use cases. So first, the disclaimer. So this is based on public sources for each company. I only work for one of these companies, so I have to go off of what they publicly say about their architecture. So if it's wrong, I either read the source wrong or they didn't actually disclose it accurately. We won't be covering every all-flash array architecture because, quite frankly, some of the ones that are out there are not all that different from traditional arrays. Other ones don't have a rich set of features, and so, frankly, their architecture just doesn't have that much to talk about. And some just aren't that well documented, right? There's just some out there that they haven't really disclosed anything about the architecture, so I can't really talk about it. Next, system redundancy. How are high availability and data protection achieved? We talked about SolidFire a little bit with this. But interestingly, this is a place where SolidFire and XtremeIO are different, actually, in how we approach high availability. Pure and XtremeIO, although they want to pretend they're very different, actually take the same approach here fundamentally when it comes to data protection. Both of them use a dual controller and shared disk shelf model. So they've got a pair of controllers connected to a disk shelf. This is what EMC calls an XBrick. This is the entire storage system for Pure. Both of those controllers can access all the drives in the shelf or shelves in Pure's model. And redundancy is accomplished by having redundant copies of data within a shelf using RAID. And that protects against loss of an individual drive. And then having redundant controllers, either active-active or active-passive. If one of the controllers goes away, the other one can still access all of the data that's on that disk shelf. If you have a disk fail, you do some kind of RAID rebuild within that shelf to restore that, either to a spare drive or to the existing capacity on that shelf. If you have a controller fail, the other controller takes over, you have to go out and replace that failed controller. If you have a shelf failure, nobody wants to talk about it. And that is a big hole in these designs, which is that if there is a shelf failure, this data only exists within the shelf. And particularly in XtremeIO's case, because they're distributing their volumes across all of their bricks, if any of the shelves go out, the entire system is down. And depending on if the data is still there or not, you may or may not have lost data. But in any case, you've got to replace that shelf to get your system back up and running. So SolidFire, as we talked about, uses a shared nothing architecture. Literally no sharing of any hardware component in the system. Everything is redundant, including the network connectivity. And importantly, the disk and controller failure are handled the same way. Most of our customers actually don't pay for 4-hour maintenance because they don't need it. There's nothing in our system that has to be replaced in a 4-hour window. The system will rebuild, keep running, and next business day is completely fine, if not longer. So comparing these two models, shared disk, you've got a minimum of 2 controllers. That can be a good or a bad thing. Actually, one of the good things about this is that it really kind of has a smaller starting footprint than a true clustered system where you typically need 3, 4, 5 nodes to get started. Hardware replacement to restore redundancy, typically when there's a failure. This one is interesting because I think these folks like to point out this part of their data protection scheme, but they don't like to point out this part. So less capacity overhead. So parity-based RAID obviously can or should have less space overhead than a replication-based scheme like we use. So SSDs are expensive. We're going to use less space. That's great. Here's the problem. Every one of their disk shelves, or every one of their systems, you've got 2 controllers. Whereas SolidFire, we have a single controller devoted to a set of disks. And they've got to make sure those controllers are sized so they can run the entire workload by themselves. So they have literally twice the controller capacity that they need to run that system, by definition. Power loss protection. So how do you protect against power failure in the system? Obviously, losing data is probably not the preferred way to deal with power failure. This isn't really a unique challenge to flash-based systems, except really 2 things. One is that the performance requirements for flash are a lot higher. So maybe some of the things you could do on a disk-based system aren't as appropriate there. And also, this is actually a benefit in flash systems because you can use this potentially to reduce flash wear. And we already talked about why just writing to the SSD is not a good option. And none of the companies really do that, although Pure actually does write to the SSD. They just have 2 mirrored SLC SSDs that they call NVRAM, but they're actually SSDs. They use a very small portion of the space, so the drive itself really never has to do any garbage collection, so it can have very low consistent latency, and also basically unlimited endurance because they're only writing to a small LBA range on the actual device. Both of those SSDs sit in the first disk shelf in the system. In the case of Extreme I/O, when you finally get it out of them, they will admit that they keep some amount of volatile data in DRAM, and they use a UPS to power the system. In power loss situations, they will then flush whatever is not committed yet out of RAM and onto the actual SSD. But that requires a couple of things. It requires external UPSs. Most people have UPSs in their data center, but they still put UPSs in front of the UPSs to really make sure it's power protected. Each unit has to be plugged into 2 of these battery backup units. This is actually, and I didn't even realize this until recently, that's actually fairly similar to VNX, except VNX uses an internal battery backup unit, so you don't really see it. So comparing these, they all work at the end of the day. SLC SSDs, slowest throughput and latency versus the other options, which are writing to DRAM, but as long as it can keep up with whatever the specs of your system are, I guess that's fine. Very low maintenance. There's nothing that really needs to be maintained with that. DRAM with the UPS, certainly the highest throughput, lowest latency. It's just going straight into the system DRAM. They're not having to copy it anywhere. Don't even have to put it on a PCI bus. Again, there are some interesting data protection issues around it with things like a kernel panic that could, UPS or not, completely wipe out your system memory. They do replicate it to multiple nodes, so I guess as long as you don't have simultaneous kernel panics, you're okay. And very simple to implement. The NVRAM, PCI NVRAM, high throughput, low latency, not quite as fast as system DRAM, but but higher than SLC flash. You've got the data protected, and it's protected from software failures as well. Again, we don't acknowledge the write until it's in that NVRAM. If the moment it's in that NVRAM we've acknowledged the write, our software crashes and you have to restart it, the data is still protected.